discussing some work with T. Daniel Brennan, who's a collaboration postdoc working with me at San Diego. And I got a little bit ahead of myself, but this is going to be kind of like an outline in the gong show part, and then I'll discuss some more details. So, well, my background is thinking about kind of quantum field theory as this mysterious thing. I think of it as some kind of mystery machine, and using symmetries, we could try to get some insights into what's happening. And I'll be discussing what 't Hooft anomalies are and why I think they're awesome. And the concrete main thing will be some new 't Hooft anomalies that arise on non-spin manifolds. And this was a beginner mistake. Okay, so we describe these anomalies often in terms of the anomaly field theory in one higher dimension. So I'll be discussing four-dimensional field theory, so I'll write down some anomaly field theories in one higher dimension. So there's some anomaly theory. The way I write it, it often has a factor of 2 pi, so I'll just write it for now. It can contain terms like a half, some coefficient, which I'll call the anomaly coefficient, and then the integral over some 5-dimensional space of Stiefel-Whitney class. And just to give some references, well, I guess there were some papers from around 2014. One was by my colleague, Kravik, McGreevy, and Swingle, who didn't write down this anomaly term, but talked about anomaly in all fermion electrodynamics, which is related to this term. And another reference around the same time were some papers by Kapustin and Thorngren. Who wrote down this kind of anomaly term. And okay, so that's one of the kinds of terms that I'll be interested in. Another example, yeah, so actually maybe I should just say, so usually if you have a theory with fermions, you need a spin structure, and then these Stiefel-Whitney classes are all trivial. And so the first examples were examples where they're bosonic theories. And so you can look at the theory on these manifolds with non-trivial Stiefel-Whitney classes. And, but then there's a generalization of that to theories which are also bosonic, but they're bosonic in some way because it looks like when you write them down initially, you're describing them in terms of fermions, but then -1 to the f, the fermion number, ends up being part of the gauge group. And so when you gauge the symmetry, you're essentially gauging fermion number. And so even though it looks like, to begin with, you have fermions, if you look at the gauge invariant observables, or gauge invariant operators, they're not fermionic. And so then you can also consider those theories on manifolds with non-trivial Stiefel-Whitney classes. And so an example of an anomaly that comes in that context, so I'll write it slightly differently. We have a term again like this, which is a half kappa of, I'll call it G for the gauge group, and T. I'll explain my notation in a little bit, but T is basically like tangent manifold. This has to do with gravity. So this is like a purely gravitational anomaly. We can think about this as a mixed anomaly between the gauge group and gravity. Again, it's over some N5. A Stiefel-Whitney class for the gauge group, and then a gravitational piece. And this kind of anomaly was discussed in 2018 by Wen Wang and Witten in the context of a theory that I'll discuss in a little bit more detail coming up, but in the context of that theory, there's basically, these two things are actually the same, because to put the theory on a non-spin manifold, we need to take this Stiefel-Whitney class for the gauge group actually equal to that for the geometry. So even though I wrote them as if they're different things, in this context, it's actually the same. And another example of the kind of anomaly that I'll be interested in is an anomaly where, again, the anomaly theory, we can write it down as some coefficient. I'll call it kappa gamma t. And we have, again, the integral over some 5-dimensional n5, some background two-form gauge field for some one-form symmetry. So this is a background. I haven't heard the ding yet, but so.
We're still on time.
Okay. There's a one-form global symmetry. And this kind of anomaly was discussed also in 2018 by Cordova and Dumitrescu. And actually what Clay and Thomas showed was they inferred the existence of this anomaly in some theories by relating it to something that had been noticed earlier in the context of Donaldson-Whittem theory. So the Donaldson-Whittem partition function has what Whittem called a curious minus sign. And so it wasn't phrased this way, but Clay and Thomas realized that this curious minus sign could be reinterpreted as a kind of 't Hooft anomaly. So this is what I would call, all of these are what I'll call 't Hooft anomalies. I'll explain a little bit more about 't Hooft anomalies. Okay, so what do we do? Basically, what we do is we compute these kinds of anomalies like kappa gamma t in many examples. And find some simple formula to compute them. And so, you know, in a way, to be honest, this is some kind of rather modest and incremental thing to just look at this in a bunch of more examples. But this is actually, you know, I think this is maybe a difference in style between physicists and mathematicians. This is usually how at least I'm able to try to make progress, is to look, you know, concretely at something in a bunch of other examples. And usually those other examples lead to some kinds of puzzles or subtleties. Certainly we've been kind of puzzling over some subtleties, and then hopefully figuring out those subtleties will lead to something new. So I'm not sure if I'll have time or confidence to discuss the things that, you know, many of these subtleties and something new, but I wanted to at least write down, you know, these computational methods and some of the examples, and then maybe towards the end I'll mention some of the things that we're puzzling over. Good. Thank you. So that's perfect timing. Okay. Yeah. So if this were a gong show, this would actually be the perfect stopping point. Ah. Okay. You're generous. Okay. Okay. Yeah. So this is kind of my outline now. Yeah. Maybe I'll skip this since I don't get to that. Okay, so yeah, I wanted to just say some words about some of these things, and I always like this picture of QFT as some kind of mystery machine. Certainly, this was the thing that got me interested in the subject. Is quantum physics is just so weird, and quantum field theory is even weirder, and you know, it's amazing that we can understand some aspects of it. Like, if you look at quantum electrodynamics, that's the most precisely tested theory ever written down in any subject. And so we can, you know, do some very concrete things, but many other things are just so mysterious. And for me, that's one of the reasons to be looking at symmetries, is because symmetries can give us some handle to gain some insight onto some of these mysteries. And you know, if we could just do the functional integral, maybe we wouldn't need symmetries. Like if someone hands you an integral that's a complicated integral, sometimes you can say, oh, by symmetry, this integral is actually 0, and so then we don't have to do it. And so a lot of what we're doing is kind of like that, where we're just avoiding doing the functional integral because we don't really know how, and so instead we'll use some symmetries to try to make some progress. Another analogy I like to think about, so quantum field theory for me is you know, the renormalization group is essential for quantum field theory. And the renormalization group, I like to have this picture that it's like water going down some mountains, and so there are all these streams. And the thing I like about this analogy is it captures universality, which is that many of these streams kind of go to the same place. And so if we just start trying to say, oh, what happens in the ultraviolet, which is like going up the mountain, like where did that water come from? It's kind of ambiguous because water might have come from lots of different places, but still we can say what happens as we try to go towards lower energy. And so when I think about QFT as this mystery machine, it's like, imagine we know where the water is at some point on this mountain, maybe we don't know where it came from at higher points, and then the machine is like, where does it end up going? And so we put in some input like that, and then we get all sorts of strange outputs sometimes. And we can't actually follow it in detail. So it's like these streams, there's some kind of fog. And so the water goes into the fog, and we don't know what's happening. And then basically what we try to do is guess. And so most of what I've worked on, you know, for the whole time I've been working on this subject is trying to come up with guesses. And so none of these guesses are proven. They're all just conjectures. But we can use symmetries to do lots of checks on the guesses. Yes?
80% of water flow is underground, by the way.
I'll keep that in mind. Okay, so we have all of these.
Before you move into the next part, can I also what N5 is? Is that just your space-time? Are you working in a 5-dimensional space-time? Or what
Yeah, so here, these 5-dimensional theories, I'll describe more like, this was kind of just the gong show part, so I'll describe more like what I'm actually doing. But what I'll be discussing is quantum field theory in 3+1 space-time dimensions, so in our physical space-time dimension. And then these anomaly theories that I've written down as 5-dimensional theories, these are just like some mathematical trick that captures some details about those theories. So one of the nice things about these anomalies is all of the connections that we've been hearing about, that they could be written in terms of this quiche theory or sandwich theory in one higher dimension. And so these are like this topological theory in one higher dimension. Yeah. And for me, it's kind of, or for everyone, it's kind of just like a nice mathematical trick to capture some things, is to write in terms of this topological theory in one higher dimension. But yeah, but I mean, the theory in one higher dimension has its own separate interest as topological field theories, I guess. Okay, so we know, for instance, there's this Clay prize problem. So let's say here, this is at the theta angle equals 0. I mean, we know from symmetry arguments that if theta equals pi, it might do something slightly more interesting. And so this is $10 to the $6 million Clay prize. And this Clay Prize is still unclaimed because, you know, what I said, we don't actually know how to show it directly, but this is what our guess is. So this gives us, so this is an example of what quantum field theory can do. We start off with this theory which has massless dynamical gauge fields in the ultraviolet. We put that into this machine, and then what it spits out is just some theory with no massless fields. And so this is some very different looking infrared theory, and that's one guess of what could happen. Other examples are we can start off with some theory in the ultraviolet, and we could get some different looking theory in the infrared, or another example is we can have one theory in the ultraviolet or another theory in the ultraviolet, and it could flow to some conformal field theory in the infrared. So a conformal field theory is a fixed point of the renormalization group flow, just like this kind of mass gap theory is a fixed point of the renormalization group flow. And examples like this are Seiberg duality. So I was just discussing with Owen the other day about Seiberg duality. It reminded me, you know, just to emphasize that this is, again, a guess. It's not proved. Maybe one of you in the audience will someday prove it. But it's a guess with a lot of cross-checks, and many of the cross-checks have to do with symmetries. And the very first cross-checks that came were using a 't Hooft anomalies. And so, and which of these it is, it depends on where you are. The general thing about quantum field theory is that many of these quantum field theories are asymptotically free, which means that if you go towards the very far ultraviolet, they become free field theories. And so since it's a free field theory in the far ultraviolet, we can actually calculate things in this limit. So in the far ultraviolet limit, we can calculate things. But then as we go down the mountain, we lose control. And then we can guess, in this case, that it's some other theory that becomes free actually in the infrared. So in some of these examples, it's like a free theory here or a different free theory here. They look very different, and some parts of the map between them are known or conjectured, but in general, the map isn't known. And this exhibits another thing that quantum field theory can do in the infrared, which is that it could flow to a theory which is a conformal field theory, which is what we would call an ungapped theory. So here, this is like a gapped theory. Conformal field theory is an example of a theory without a gap. And so this is another thing that quantum field theories can do in the infrared, is they could go to a conformal field theory. And then also there are examples where which isn't a renormalization group flow, but we can have like a conformal field theory, might have a conformal manifold, and maybe we can move to some other point on that conformal manifold and get some other conformal field theory. And this is like what n equals 4 S duality does. And again, this is another conjecture. So we have all of these different conjectures. Okay, so one check on many of these conjectures are from anomalies. And so, yeah, I wanted to distinguish. A lot of the things I'm talking about are based on sort of conversations with people in the, over dinner and things. So there are different kinds of anomalies. Maybe from the point of view of a mathematician, maybe they're sort of roughly the same and you could forget about this distinction. But for some of us in physics, like this distinction between the different kinds of anomalies and the names is kind of important. And so here I'm getting to what 't Hooft anomalies are. But so one example of an anomaly in 4D quantum field theory, we can have anomalies in different dimensions. One example of anomaly in 4D quantum field theory is an anomaly that can be computed perturbatively by a Feynman diagram, which is a triangle diagram, where we have a gauge field, and a gauge field. And so there's some anomaly that in physics we draw this kind of picture to remind us of the calculation that we do to do it. And if this is a gauge theory, we demand that this thing is 0. Otherwise, the gauge theory would be inconsistent. And so this is an anomaly that we might call the bad kind or something. I mean, it's not really bad, but we want it to be 0. And so you could check, for instance, if you look at the standard model, there's this SU3, SU2, U1, and you can check by some non-trivial checks that all of these anomalies are 0, and so then that actually makes us happy that we ended up getting 0. And this is also what led to, like, for instance, this superstring revolution. Was Green and Schwartz looked at some 10-dimensional supergravity theories that came from string theory, and they showed that for certain gauge groups, like SO32 or E8 times E8, you can get 0 anomaly, and then that made everyone very excited that these theories actually make sense. And so this is one kind of anomaly. We call this like the gauge anomalies. And actually, if it's not 0, there's a way to fix it. So if it's not 0 as a 4-dimensional quantum field theory, it's just dead. It doesn't make any sense. We have to do a functional integral over the gauge fields. And when we do that functional integral over the gauge fields, we'll basically get 0 if this thing is non-zero, and so it just doesn't make sense. But there's a way to fix it, which is by anomaly inflow, which is to say that it's not really a 4-dimensional quantum field theory. Maybe it's just the boundary of some 5-dimensional theory. And then the fact that gauge invariance is broken on the boundary is really just the statement that some currents are flowing into this 5-dimensional bulk. So that would be, like here I mentioned that these 5-dimensional theories are just a mathematical trick. That would be a case where actually the 5-dimensional theory is kind of crucial. It's part of the theory. But usually we don't do that. I mean, we don't think that we live in 5 dimensions, and the fact that these anomalies are all 0 for the standard model tells us we don't have to think about us, that we're secretly living in 5 dimensions. We might be, but it's not forced by anomalies. So this is one kind of anomaly. The first kind of anomaly that was discussed are what are called the ABJ anomalies. And actually, there were some really fun new insights about the ABJ anomalies that Kantaro and Clay wrote about, and also Xu Heng and collaborators. And so for those who are staying next week, you'll hear more about the ABJ anomalies in that context. This is for Adler, Bell, and Jakif. And these ABJ anomalies arise when we think about a triangle diagram with a flavor symmetry, which is a global symmetry. So here, G is gauged, which means that when we do the functional integral, we're integrating over all gauge fields. Whereas here, F is global. So since it's a global thing, we could still couple it to the currents here, and then we can write down our partition function is a function of these global currents, but we're not integrating over it. And what this does is it tells us that for G non-abelian, the F symmetry is broken by instantons. In fact, Adler, Bell, and Jakif studied this in like 1969 or something, and it was right around the same time as the Atiyah-Singer papers on the index theorem for the Dirac operator, and it's basically, the same thing in a way. So what happens is that if you look at an instanton, so this is supposed to be some picture of some kind of instanton configuration of the gauge fields. The Dirac operator has Fermi zero modes, and so we should think about attaching these Fermi zero modes to the instanton. And so when we do what happens here is that when we do the functional integral over the fermion fields, so here all of this is some functional integral with e to the I action over h bar. When we do, basically, let's say it this way. When we do the functional integral over the gauge fields, we have to include these instanton sectors. And then, because then we'll get these extra interactions associated with this instanton. These interactions are called actually the 't Hooft vortex. So 't Hooft's name is on all over this kind of stuff in different contexts. So this is the 't Hooft vortex, and it has these fermion zero modes attached, and then that violates the symmetry. Now this kind of symmetry arises for a flavor group which is a U1 symmetry, because there's like a trace over the generators here, and if this were a non-abelian generator, its trace would be 0, and so we wouldn't get this. And so what happens is this breaks U1 anomalous to some discrete subgroup. Let's just say there's some Zn, which is some symmetry that's unbroken by all of these Fermi zero modes. Okay, so this is another kind of anomaly. And this anomaly also, I should say all these anomalies lead to all sorts of nice things. So even though the symmetry is broken, that still makes us happy because, for instance, one thing that 't Hooft showed is that this solves a puzzle, because if you have spontaneous symmetry breaking, then you get some number of pions, which is related to the number of broken generators. And if this anomalous symmetry had actually been a symmetry, there would have been an extra pion that no one saw. And so this solves the eta prime U1 puzzle. It explains why we don't see this extra pion. It also helps understand the decay of pi 0 to 2 photons, which I know that Shuheng will talk about next week in the context of these non-invertible symmetries. So it does lots of good things.
Are the gauge anomalies, are they also in this one higher dimension? It can be treated in this sandwich quiche sort of picture, or it's a different?
These ones?
The first one, the gauge anomaly.
Yeah, they can. But what happens there is that the bulk theory is never topological. So yeah, you have to really have dynamical gauge fields in the bulk, and so yeah, so that's right. Yeah, thanks. Okay. We could also look at gauge flavor. This leads to two-group global symmetry. So this anomaly is just essentially some coefficient kappa, and so kappa is basically what you would call the Postnikov class. So it's some non-split two group. Just an aside. The main thing I'll be discussing are the 't Hooft anomalies, where all of the three things are flavor symmetries. And there's a lot to love about the 't Hooft anomalies. So these are supposed to be hearts. One thing to love about them is they are invariant. Here I'm writing some kind of example of a 't Hooft anomaly, but actually the ones that I'll be discussing have nothing to do with these kinds of triangle diagrams. So these kinds of triangle diagrams are for the kind of old ones that were discussed a long time ago, and the more recent ones. Yeah, actually, maybe I should just take a minute to say that part of the motivation for the project that we're looking at is that unlike these ones where you could compute them from these triangle diagrams, the ones that we're looking at don't have a simple calculational way like this to compute them in general, and so we've been looking at some cases where you can do some tricks to write down calculational ways to compute them. But so here I'm kind of just using this as a picture for the kind of anomaly that I'm talking about, but the actual ones I'll be interested in don't have this kind of description.
So you mentioned that the gauge anomaly, if you put it on the surface of some higher dimensional theory, it has to be a dynamical gauge theory.
Yeah.
Then that's also the case for these ABJ anomalies?
No, the ABJ anomalies basically just tell you that this thing that you thought was a U1 symmetry is actually just a discrete symmetry. And there is a way sometimes to save the non-discrete part, and so that's like, for instance, what Clay and Cantaro and also Shuheng and collaborators looked at, and that's in the case where G is an abelian symmetry, or more generally, if you don't have these instantons. So what happens? What this thing tells you is that the divergence of the current of this is like FF dual for these things, and so. The first thing that people tried when they saw that was to just write FF dual as the divergence of like a Chern-Simons type current and bring it to the other side. And that works fine in perturbation theory, but non-perturbatively the instantons just break it. But
Can you keep, if you kept G background, then it would be a mixed anomaly between
yeah.
two symmetries?
yeah, if G is a background, I would say that's like this case I'm discussing here where it's really an 't Hooft anomaly.
Yeah, but then you can view that as the surface of a bulk and then gauge G everywhere. And so you could view this as something that lives on the boundary of a dynamical gauge theory.
Yeah, maybe there's, I'm trying to think if, you could certainly do that. Yeah, I'm not thinking of like an application where it's helpful. I mean, if you didn't want that bulk theory, then you would just say this U1 is just broken to some discrete subgroup, and then that's not really a big deal. But if you really wanted to keep the full U1, maybe you could do something like that. But I'm not thinking of what it actually buys you. But maybe there's something. Yeah. Okay, so one thing nice about 't Hooft anomalies is that they're invariant under any symmetry preserving continuous deformation. So for instance, if you can add mass terms without breaking the symmetry, they're invariant under that. If you want to dial H bar, they're invariant under that. So you don't see them if H bar is 0, but for any non-zero H bar, they're totally independent of H bar. In fact, that's why they're one loop, is because they're completely independent of H bar. So they're independent of any kind of continuous deformation that preserves the symmetry. And another continuous deformation that preserves the symmetry is, assuming that the symmetry isn't broken, like in this case, is renormalization group. And so that's the main application of these 't Hooft anomalies, is that they're invariant under the renormalization group. So in all of these pictures, if there's some kind of 't Hooft anomaly that you can compute in any limit, it has to be the same 't Hooft anomaly everywhere. And so that gives these kinds of checks on these dualities. So it's RG invariant. And that's a great crutch for trying to guess where the renormalization group flows end up. If there's some non-trivial 't Hooft anomaly, then you have to match that. So these were originally called 't Hooft anomaly matching conditions by, if you have some kind of scenario like that, you have to check that they match.
Could you remind us what the theory is for the two group? What theory gives you that two group? Global anomaly.
Yeah, so here, since there's only one vertex here, this has to be, in 4 dimensions, this would be an abelian theory. There are analogs in higher dimensions where it doesn't have to be abelian, but in 4 dimensions, it's a U1 gauge theory. And you can have this kind of situation if you have fermions that transform under some flavor symmetry. Like for instance, if you looked at QED with NF massless Dirac electrons, there would be an SUNF left and an SUNF right global symmetry. And so if I put in here like SUNF left and SUNF left and the U1, we would get this as non-zero. And so that's a perfectly good symmetry. And then actually, this was an example that Clay and Thomas and I were looking at mainly because it's kind of like a warm-up version for trying to understand better some things in a paper by Cantaro and collaborators. And we became very puzzled about if this is a problem or not, given that it's a gauge current. And in the end, it's not a problem. What happens is that there's a one-form global symmetry from the magnetic symmetry associated with this U1 gauge group. And then that one-form global symmetry mixes with like the SUNF left with some non-trivial two-group structure and Postnikov class that's related to this coefficient.
How does it decide to mix with left rather than right?
Yes, sir?
How does it decide to mix with left rather than right?
Yeah. So it's actually it's like the left minus the right piece is the one with the anomaly, and so yeah. So you could write it in terms of either left or right, but if you looked at like the diagonal one, left plus right, you would get 0 because that diagonal one you can actually add mass terms for, and so this anomaly ends up being 0 in that case for the diagonal one. Okay, so that's.
And can I ask, is it obvious from the definition that these Tooft anomalies are invariant under symmetry preserving continuous definitions?
No, it's not at all obvious. And so when 't Hooft first wrote down those conditions, there's actually not a paper. It's based on some Carget summer school proceedings, and it took a long time for people to actually believe that it's true. And he had some argument in terms of, basically if this thing is non-zero, it's an obstruction to gauging it. So if we were to gauge it, it would be inconsistent. And so then the idea was to add some spectators that cancel this anomaly that are otherwise decoupled. And then in that case, you could have gauged it. And so that should be true always along the RG flow. And so you should get the same answer in the infrared. And then you could say, well, those spectators were kind of just going for the ride. And so that tells us that the anomaly has to be the same. That was 't Hooft's original argument. So it's quite hand-waving. But basically it's right.
That argument doesn't work for your much stronger conclusion that which is supposed to be able to do any continuous transformation.
Yeah.
Which must boil down to the assumption that the anomaly is somehow topological.
Yeah, right. That's exactly. That's what I was about to say. Yeah. So in the end, what people eventually realized was that all of these anomalies you can think about in terms. Yeah. In fact, I think this was maybe my next point was that all of these anomalies are related to this kind of picture of one higher dimension, and so all of them you can think about. Yeah, so the next thing to love about them is this connection between like our quantum field theory in d space-time dimensions as being like the boundary of some TQFT or in D+1 dimensions. And so if it's a, yeah, so basically all of these 't Hooft anomalies are encoding the topological data of this topological theory. And so whatever is happening with this RG flow on the boundary, that topological data can't really change. In fact, many of these coefficients have to be quantized to satisfy consistency conditions. And so if they're quantized, they certainly can't depend on any continuous parameters. Yeah, so this is the part that we've been hearing a lot about, or that you know, we discuss a lot in this collaboration and also in this meeting. Okay. And so, yeah, so this is unphysical, but a great trick. I mean, maybe there's some physical way to think about it, but you know, I think about this higher dimensional theory as basically some beautiful trick. So unlike the gauge case where we would have had to actually make those dynamical gauge fields, here they're non-dynamical gauge fields. They could be like topological gauge fields. Okay, and another great thing about 't Hooft anomalies is that you can often rule out symmetry gapped phases. Like in this example of Yang-Mills, the infrared theory here, confinement in a mass gap, has no 't Hooft anomalies. And so if the UV theory had 't Hooft anomalies, which it doesn't, that would show that this first scenario is impossible. And so often you can rule out symmetry preserving gapped phases, and so that tells you then that the infrared theory has to flow to something kind of interesting. There has to be either spontaneous symmetry breaking or some ungapped modes. Like in all of these examples with Seiberg duality, they're non-zero 't Hooft anomalies. And so we know in the infrared it can't flow to a gapped phase. There has to be something that matches the 't Hooft anomalies, and then you can try to write down something that does that, and that's what the duality does.
Sometimes it can be gapped, but it could be a TQFT.
Exactly, yeah. So that's why I said often, yeah. Because, so for the discrete, for continuous symmetries, you can rule out symmetry preserving gap phases. For discrete symmetries, sometimes you can and sometimes you can't. And so actually, like Cantaro and Clay had two very nice papers where they explained when you can and when you can't match it with. So for discrete symmetries, sometimes you can just match them with some TQFT in the infrared. And if you can match them with a TQFT, in a way they become, these anomaly matching becomes less constraining, because you can just say, well, if it doesn't match, we'll just throw in this TQFT. I mean, it might be very interesting for condensed matter applications, but in terms of RG flow, it's less constraining. So yeah, so I would refer to Cantaro and Clay's paper for when it does or doesn't. Okay, and then another great thing about 't Hooft anomalies is that they're computable. Exactly. Often. But in all cases that I know, they're exactly computable. And basically, like if we have any kind of theory, for instance, that's related by RG flow or by any changing couplings to a free theory, like if we look at, for instance, QCD. QCD is related by, if we go towards the far ultraviolet and turn off all of the masses, well, it doesn't matter if we turn off the masses or not, but let's just turn off all the masses. So if you turn off all the masses, there are some nice 't Hooft anomalies, and then the theory is asymptotically free in the ultraviolet, so you can just compute it from a free field calculation. And so that's what these triangle diagrams are encoding. And actually, these triangle diagrams more generally are encoding the fact that for anything that's for continuous symmetries, these 't Hooft anomalies are actually related to index theorems in D+2 dimensions. And so, like, there was a beautiful paper of Alvarez, Gomez, and Whitten that wrote down how to write down these anomalies that you could, in principle, compute determinatively from index theory in D+2 dimensions, and that's what's called the descent procedure. And basically, what you get in D+2 dimensions would be like, for instance here, if this is a non-abelian flavor symmetry, we would get some coefficient times the third Chern class for the background gauge field. And that third Chern class you write as D of a Chern-Simons term, and that Chern-Simons term is the bulk topological theory that includes the anomaly. And so often these things are very computable. So, wow, I'm almost out of time. Yeah, okay, so this is all some long-winded motivation for why we wanted to be able to compute these other kinds of 't Hooft anomalies. And let's see, given the time, maybe I should skip a bunch of stuff.
In the cases you are computing the anomaly, do you have to worry about first computing like a fractionation class to fix the anomaly, or does it matter? Like if you have like some one-form symmetry, I guess we have to worry about fixing the fractionation class first before computing the anomaly, right?
So yeah, so if these are all global symmetries, then yeah. So in general, what we want to do. So here I was all discussing all of this just for zero form symmetries, and so we could also write down 't Hooft anomalies also with one form symmetries, and that one form symmetry can lead to these kinds of fractionalization, and right. So there, what we would do is we would include in the anomaly theory also the background gauge fields for the higher form symmetry, and that would include like this. Fractionalization effects we can include with background gauge fields. Yeah. Okay, so yeah, maybe in view of the time, I'll skip a bunch of stuff and maybe just jump to just to jump to an example of the new, let's say, old SU2 anomaly. So the old SU2 anomaly is, suppose you look at an SU2 gauge theory with, let's say, one flavor of in the fundamental. So we could write this fermion as psi alpha C, where alpha is a Lorentz index. It runs over two indices because this is a Weyl fermion, and this C is a color index that runs over 1 and 2 because it's in the fundamental of SU2. And this is a theory where we can't write down a mass term. And so if we wanted to try to write down a mass term, we would take, for instance, like psi alpha, psi beta, and let's say here we have color D. And if we wanted to write down a mass term, we would try to write down a gauge and Lorentz invariant operator like this. But we have to do two things. We have to make it Lorentz invariant. So we have to anti-symmetrize in these alpha and beta indices, and we have to make it gauge invariant. But then it would be symmetric, and because these fermions should be anti-commuting, we would just get 0. So this is just 0, which tells us that this might be an interesting theory, because we can't write down a mass term. Maybe it has some interesting anomaly, and in fact it does. It has a gauge anomaly. So this theory is just inconsistent. So this is the old Witten SU2 anomaly, and Witten showed that it's related to pi 4 of SU2 being Z2. And if this were instead SUN instead of SU2, we would just say it's obviously a bad theory because we could compute the triangle diagram, and we would see the triangle diagram is non-zero. But that triangle diagram for the SUN case involves the third Chern class, and so it involves the cubic Casimir, and SU2 just doesn't have a cubic Casimir. And so SU2 kind of looks like a special case, but then this basically says it's actually not a special case. The theory is also inconsistent. And Witten had, in his original paper, had an argument for why it's inconsistent, which is basically from the Dirac operator in a 5-dimensional theory. On the mapping torus. And so the idea of this 5-dimensional theory is that, basically, so this is a picture from Witten's paper. If you look at the Dirac operator, its eigenvalues are real and skewed, skewed diagonal. And if you were to look at the fermion part of the functional integral, you'll be getting like a square root of the determinant of the Dirac operator. And so the problem is because that square root can have a plus or minus sign. And then if you wanted to define it, what you could do is you could say, oh, let's just take the positive eigenvalues and forget about the negative ones. But then what happens is that you can move in some parameter space, let's call it T, and if you move in that parameter space, you can see the fact that there's these pi 4 of SU2, and then there's like some crossing here, and so then you pick up some minus sign, and then you see that the theory just ends up giving you 0 in the functional integral. And so this mapping torus is basically, we take our 4-dimensional space, and then we introduce some extra coordinate, which is like this T coordinate. And so here's our 4-dimensional space again, and then we glue it together. And that shows, like for instance, after you do this gauge transformation, if by this procedure you get something where you can show that the path integral picks up a minus sign, then you show that there's this anomaly. And so that's what Witten showed. And so the mapping torus in this case is some 5-dimensional space, which is basically M4 times a circle, and maybe we can write it as like some kind of semi-direct. And it's non-trivial because as you go around the circle, what you can do is you can put in a -1 to the f. And that -1 to the f makes makes it so that it's like the Witten index on this S1, that only the Fermi zero modes contribute. And then basically you reduce this 5-dimensional Dirac operator to a 4-dimensional Dirac operator on M4. And the upshot of all of this is that you can see the anomaly from the 4-dimensional Dirac operator, which is to say, just from looking at a 4-dimensional instanton. So there's an instanton, and this was noticed before Witten's paper, that a curious thing about this theory is that the instanton would just have one fermion zero mode. And so the instanton is not gauge invariant and it's not Lorentz invariant, and that looks maybe problematic. And what Witten showed was that in fact it is a problem, and related, it ends up showing that the theory is inconsistent. And so at that point, you could kind of, if you want, forget about this mapping torus construction and say, oh, let's just look at an instanton. We just look at the Dirac operator and then see that there's this minus sign. Okay. Maybe. Okay, so the new SU2 anomaly. So we know from the Difreed theorem that these anomalies for non-perturbative anomalies we could describe in terms of cobordism groups, and so we can think about this old anomaly as related to the fact that there's some Z2, and that Z2 is basically just saying here, we pick up this minus sign. Actually, for general NF, what happens is that this tells us NF had to be even. And so if you look at the case of NF odd, it's inconsistent. To make it 0. And but if you look at the case without spin structure, then there's actually a Z2 plus Z2. So there's a new Z2. And so we can ask what's this new Z2? And this isn't what we asked. This was what Wen, Wang, and Whitten answered. And they showed that this thing can be non-zero, for instance, for a cousin of this theory, where we have SU2 with psi alpha not in the j equals 1/2, but in the j equals 3/2 representation of SU2. And so we need to do that on CP2. And CP2 isn't a spin manifold, and the way that you can make sense of it, even though there's a fermion, is because of the fact that minus 1 to the f acts the same as the center of SU2. And so when you gauge SU2, you're gauging minus 1 to the f. And so even though this theory looks like it has a fermion, it's actually a bosonic theory. And you could put it on CP2 by taking W2 of the tangent manifold equals to W2 of SU2 gauge. And then you get these anomalies that I wrote down. So the theory actually has an anomaly, which is where the 5D theory has this W2 of SU2 gauge. And this is kind of an 't Hooft anomaly. And so this 't Hooft anomaly isn't a triangle diagram, but even though it's not a triangle diagram, what Wen, Wang, and Whitten showed was that there's sort of an analog of this calculation that allows you to read it off from an instanton diagram, or from a it's not really from an instanton, it's more from like the zero modes of the Dirac operator in the appropriate flux background. And so that gives a nice calculational way to compute this. And
So you're doing SU2 gauge theory, but are you saying that SU2 also just happens to be the flavor symmetry that you're studying, or?
No, yeah. So in this case, there's no flavor symmetry. So there's just one. There's one flavor of this. It has a color index. I could write the color index as like C1, C2, C3. You could symmetrize.
So it's the anomaly for what? For what kind of symmetry?
So it's a mixed anomaly. It's really a gravitational anomaly. Like if you put the theory on CP2, it's inconsistent. But you could also picture it as a mixed anomaly between the geometry and the SU2 gauge group.
Okay, sorry.
And yeah, so this is SU2 gauge. And the case that actually we're interested in is similar to this, but where it actually is a global symmetry. And so all of this was supposed to be part of like I'm afraid I'm running out of time, but all of this was supposed to be kind of just like a warm-up for the case where it's a global symmetry, but in their case it's a gauge symmetry. And basically what happens is that if you put the theory on CP2, then there's an analog of this mapping class construction where, or mapping torus construction, where you put in here an isometry of the background of CP2. And so this phi, what it is you introduce some phi hat, which is complex conjugation on CP2 with a Weyl symmetry to preserve the fluxes. When I say the fluxes, we need this W2 of SU2. So if the tangent, and if the geometry is CP2, this thing is non-zero, and so there's some fluxes in this SU2. And so this is some kind of symmetry of the theory, and you can look at the mapping torus on this. And what you find when you do that, or what they showed, is that the zero modes of the four-dimensional Dirac operator are in two-dimensional O2 representations, where this O2 is related to like a U1 and SU2, and with some kind of like semi-direct with this phi hat action. And this, oh, my time is up. Okay, yeah, so maybe I'll just quickly write the formula. So you get basically some nice formula where this kappa is 1/2 of the number of zero modes, and the number, so this is the index, and the index we can write as a sum over a bunch of charges. There's some nice formula that we can write. So it's very concrete, where these are related to charges when you write it in this flux background. And so what we did is to apply this kind of thing to the case where it's not a gauge symmetry, but it's a global symmetry, and then compute this index and see when this anomaly is zero for a bunch of different examples, and then try to study the implications of that for RG flows and matching to possible infrared phases and things like that. And yeah, sorry to have spent so long on the review part and not to really get to the need to talk, but I guess I should stop.
Thanks a lot. We have time for a couple of questions.
I'm actually a bit confused here because I thought like BG would be relevant if G is a global symmetry, but here you put omega SO of BSU2.
Yeah, maybe I wrote
SU2
it
is
wrong.
Gauge.
Yeah, maybe I wrote it wrong. Yeah, SU2 is gauged.
Okay.
Indeed, yeah.
So do you maybe just mean omega 5 SO or something, and not the BSU2?
Yeah, maybe I don't want this. Yeah.
No, it's definitely B. The tangential structure of the equal spacetime. in cross BSU2.
Yeah, so I mean, basically, the way I want to think about it is we can write down, you know, this W2, W3 anomaly that I wrote before, but I'm not sure what's the right way to see it in terms of this.
Because when you wrote omega spin BSU2, I would have said that's the relevant thing to look at when SU2 is a global symmetry.
Yeah, that's what we're
But
doing
then
later.
but when SU2 is a global symmetry, in both cases, it's fermionic theory. So it's, I just don't understand why you should go to SLL.
Another way to define a Tuft anomaly is a failure for the partition function to be invariant when you couple to
Yeah.
a background gauge field.
Yeah. So actually, yeah. So what I was, maybe I can use this opportunity to kind of say a little bit more of the talk. So, so basically, what we were looking at is the analog of this, where it's a global symmetry, and then in that case, the theory is not bosonic. But what we can still do is we can turn on background gauge fields for that global symmetry, and that's basically what happens like in the supersymmetric context, where you do what's called this topological twist, is you turn on background gauge fields, and the background gauge fields effectively allow you in a way to think about like a redefined version of the stress tensor, where you change the stress tensor by the current that you're twisting by to make everything effectively bosonic. And so we're actually interested in analogs of this where it is a global symmetry, but you can still put it on, for instance, CP2 by using the fact that -1 to the f is in the center of this global symmetry, and then you can twist by the global symmetry to do it. So that's the examples that we're looking at. Yeah, thanks.
Okay, so before thanking the speaker again, let me suggest that we have a 5 minutes break before we go to the last talk for this morning, and let me remind you of the talk before dinner. Okay, thank you very much.